Today we're going to start on chapter 9 in this book. And even though it is a new topic, we're going to start out in the beginning of extending a lot of the earlier algorithms we had with multi-agent learning um, that we had from tabular problems and start incorporating approximation techniques with them. So we had already looked um, I believe in chapter 6 of the book at simpler problems where we can adapt techniques from reinforcement learning, where we estimate values in states. And there was a whole bunch of techniques we developed, including independent learning and then, agent modeling and eventually other more complicated game theory type solutions. But all of those techniques required a type of approximation where we estimate values for states in the environment. And those individual values are all independent. So we basically have like a lookup table of different values like corresponding to data that we've collected. And the problem is, in order for that technique to work, we have to collect data on every state in the environment because like all the states are linked, and to understand what optimal behavior is, we need to have good estimates of the entire environment. And if an environment's big enough, we may not even be able to visit all the states even one time in a reasonable training budget. And to really do well, we have to visit states way more than one time to get good estimates. So in that situation where we have a problem that's large, we need to turn to some sort of approximation technique where we use a function that is designed to try to generalize information across states. And if the state space is behaved well enough, hopefully if we get information of certain states, there is some sense that like nearby states could have similar values, be related in some way. And this all really depends on how good the approximation function is at mapping states that are close together in some kind of meaningful way. Now, if we have a problem like here, I'm just going to show I'll probably talk near the beginning about this particular problem, or just so you have a concrete example in mind before we get going. But this grid, this is mentioned, this is one of the key examples in the book. This is a common test problem for multi-agent learning. And it's called this level-based foraging example. So there's some kind of open grid where the agents can move. So here in this, I've labeled the agents in blue. And then there's items, or sometimes it's called food. But these are things that the agent can collect. So the important point is that everything, all the agents and all the items in this problem have a level associated with them. And the way the problem works is that in order for an item to be collected, and that's the only way that you can get reward in this problem. So like the goal is to collect the items, but the items cannot be collected unless the agent is adjacent to an item. So every item would have 4 squares that are adjacent to it. And the agent has to select, the collect action. So it has different actions available, like it can move in the different directions, it can do nothing, or it can try to collect an item. And the added complexity of this is that an item can only be collected if the agents attempting to collect it have a combined level that is the same or greater than the item level. So like if this agent is level 1, it could collect this item on its own. But this item, it cannot collect on its own. And it would require both agents to cooperate and position themselves adjacent to the item, and then both attempt to collect it together. So this task, like the complexity of this task changes with the size of the grid and with the number of agents and items. So this task also is typically designed where an episode will begin in some random state where we have to spawn the agents and items onto the grid. And then an episode will end when all of the items have been collected, at which point we can start a new episode. So the items in general will change position. So I there's this note later in the chapter on the complexity of this task, and we could just talk about it in terms of like what distinguishes a tabular problem from one of these problems that requires approximation. So earlier in the book, we had a version of this problem where there was an 11 by 11 grid, two agents and two items. And actually I had looked at it here in one of the previous sessions. We had looked at it. So this was the earlier problem that we had. And this problem is also simplified in that it always, this is always the initial state of the problem. So the two agents always start in the corners here, and then there's two items. One of the items can be collected by either agent. The other item requires cooperation between the two agents. So this was an example of a problem where this state space, also because the items don't move, like they always spawn in the same position, this is a pretty small state space. Like we really just have to consider all of the positions of the two agents. So it's like an 11 by 11 grid. So each agent can be in any one of these available squares, and then the other agent can be in any other available square, not occupied by the first agent. And then this was in a problem where we saw we could solve it exactly, where this is like the optimal solution where the agents, I mean, it's a pretty simple solution, but just the final step is the two agents coordinate together and collect the item in this position. So when I made like the tabular version of this environment, notice like what makes it tabular again is that the state space is small. So here it's 57,000 states. Yeah, the way we're like you can just enumerate all of these, right? And then in the book, what do they say? Yeah, 42,000 states. So like it's not I'm not sure what the discrepancy is, maybe the way. I think I probably counted more states cuz I think probably the difference is I add like I have terminal states that don't really exist. Like really the only way both items can be gone is in this state. But I think I also included like all the states where the agents are positioned in different places, but the items are gone, which will never actually happen in the problem. But you know, it's all it's just easier to do it that way than think about what states you have to exclude. So this problem size is completely manageable for a technique where we, estimate individual values. And in fact, like that's what's being shown here is one of these like one way to solve it. Like this is an exact solution where we have just like there's 57,000 individual values that contain all the information about how to solve this problem. So again, like this is what, like, in order for something to be classified as a tabular problem, it has to be like, we have to be able to store this sort of information, both of the states themselves, and also like our solution will have to store these things. So does that make sense to everyone about like what, like how small a problem has to be for to use the like earlier techniques in the book?
Yeah, I mean, I'm following this. I'm sure other people are.
Okay, great. So now for this chapter, we're concerned with larger problems. So One way to make it larger, we can make the grid larger. So actually, if we make the grid 15 by 15, which is what, is sort of approximation examples we're going to look at. And then we also have, like, let's just say, as in one example, we have two agents and two items. So the same as the first example. But now we allow them to spawn anywhere in the grid. And this makes the problem considerably bigger. So they estimate about 5 billion combinations of where the agents and items can be. And then they also consider a case of 3 agents and 3 items. And this is now, 300 trillion possible states. So these are examples of problems where it would be, fairly impractical to solve this as a tabular problem. But yeah, we can look at what this sort of environment looks like. So now, if I make the environment like the unrestricted environment, notice now this version doesn't have a list of states, right? Because the state space is too big. We do have a function that we can use to transition between states. And then there's a list of the actions that each agent has available. And in this case, both agents have the same actions. They have the 4 directions of movement, the collect action, and the no op action. So we can see if we run an episode in this environment, that means that we just let the agents behave until it terminates. Or in this case, I've capped it at 10,000 steps. So this problem is hard enough, just this version of the environment where it can't, random behavior won't solve it within 10,000 steps. We can see just the agents will move around, and in general they may collect some of the items, but we could see the reason why this is failing is because some of the items here require coordination. So the items that all these 3 items could be collected by just this single agent of level 2. And then the thing that's going to be hard about solving this problem is the part where the agents have to coordinate together. And that's going to be the challenge. And that's why after 10,000 steps, these items are going to remain uncollected, because it's unlikely, that just randomly these 2 agents would coordinate together. So whatever. This is a version where I've spawned 5 different items. So the test environment they talk about in the book, there's 2 tasks, sort of a simpler one and a harder one. So the simpler task, we just spawn 2 agents and 2 items in the same grid size. And then we try 3 and 3. So, if I keep clicking this, basically, it's going to keep initializing a new environment. Or not a new environment, a new initial state to the environment. So we can see that every time it spawns, the agents and items spawn in, random places. Now, so I've just because this is a fairly simple thing to implement. It was one of the first things I had looked at when I was sort of building up how I wanted to structure the environments and what they look like. So I use this as an example. This is an earlier notebook we had used in one of the earlier sessions. And this is, my version of this level-based foraging environment. And I have sort of the actions, and the state is then what we're going to use to learn from. And this is the information available. If the agents, if they don't have, partially observable information, they just have access to everything. What they would have access to is the positions of all the agents, the positions of all the items, whether the items have been collected or not. So this is this will be a Boolean flag. And then the levels of the agents and items. I did it this way instead of removing items, because this way, if you're doing stuff where you're assembling states, it's kind of nice to have a standard size of everything. So this way, for a particular environment, the actual state will be exactly the same size, regardless of whether items have been collected or not. It'll keep saving the information about where the items used to be. And then there's just this flag about whether they've been collected or not to turn them on and off, basically. The other notable thing about this, so there's all these helper functions like to check if someone's adjacent to an item, and then the actual reward the agents get is also sort of normalized based on the maximum level, so that if all the items are collected, basically like the final reward for everyone is 1 if you add up everything. So they'll get a percentage of, like, if there's a bunch of items with higher levels, it all gets normalized both to the maximum item level and the number of agents in the problem. The note also that with the actions, right? There's the 4 directions. There's collect, and there's the no-op action. Now, the collect action is just a single action, right? It's not like that. There's no way for the agent to say which item it wants to collect. So actually, another important part about setting up this environment is the items have to be spaced out far enough that an agent is never next to 2 items at once, right? So you have to sort of, if you spawn an item, you have to create like a bubble around it where no other item can spawn within that bubble. Like, otherwise, if an agent is next to 2 items simultaneously, then the collect action is ambiguous, and that is a problem for the environment. So the other thing that you probably want to do in this case is, when you spawn items, like, I have a maximum level for the agents and items, so they'll spawn with random levels. But you want to make sure that once the agents spawn, you take the sum of their 2 levels or 3 levels, however many there are, and you don't want to spawn an item which exceeds that sum of the agent levels, because otherwise that item will be impossible to collect, right? So if both agents happen to spawn with level 1, then the maximum item level should be 1 in that, or should be 2 in that case for this environment, because anything higher than 2 would not be collectible by all the agents. If you have a lot of agents too, like, there's also only 4 possible sides of an item can be occupied. So really you want to cap the item level at the largest, the highest combination of any 4 agents, a subset of 4 agents. But that's a little complicated. I didn't bother to worry about that because we're not really looking at problems where there's more than 4 agents at this point. So eventually we're like, the state initialization is the part where you have to be careful about spawning spawning the items and making sure that they are not too close to each other. So here is like, I sort of create like these excluded positions that an item can't spawn in. So if you're curious about the book and its code base, this is the part of the website associated with the book, and they mention their code base has different components, a lot of which is like related to other open source projects. So they do talk about this level-based foraging environment, where they have like experiments and tests they've run with it. They have these like text-based flags to define how large the grid is, how many players there are, how many items there are. But actually, what they're using is this repository, which is, I think that they're using like the OpenAI Gym interface, but with some modifications, because Gym primarily isn't used for these multi-agent problems. So I think they have some like special functions around it. They also have their own visualization tool for this problem. And you have to install it with pip, and then the actual, like, this is the whole repository for the level-based foraging environment. And it has it's a lot of lines of code. It has to sort of interface with all this gym stuff. And when I first looked at it, I could say it is a little hard to find like where the actual stuff happens in it. There's a lot of layers of abstraction. Um, but eventually, if you look deep enough, you can find this information which is sort of important, like especially for the multi-agent problems we're looking at. This is the observation space they're defining for the problem. And there's these different flags that control whether an agent gets access to all the information about the environment or it has limited information in some way. Like maybe it can only see a certain region around the agent. That's one sort of restriction. Or it has a limited history that it can see. But, if you look in here, you could see how these if statements control whether, how much of the information in the state that it can see. And there's also, oh yeah, these tests. But yeah, you can find in here like the initialization functions. Somewhere, I don't know. You can see like this is like it's a lot of lines of code for setting up the environment. Maybe it's oh no, not that. Yeah, I think most of it though is contained within this environment.py file. But you can see also, yeah, like the action space here, the same as the one I have. And then, yeah, oh yeah, here's the initialization function. So where we control, the player levels, the food levels, everything. In their case of setting up the environment, they also, it looks like that they have these like attempts that they run up to actually place everything. And I think they just have the thing fail. Yeah, here's like their spawn food function. So this is like what would set up the environment. I assume make sure that it's all separated enough to not cause a problem. But I guess instead of actually excluding the states that should be excluded, what they do is they just basically randomly spawn it, and hopefully within 1,000 attempts of this, it meets all the necessary criteria. And if not, I guess they just don't spawn all the items that would normally be spawned if they can't manage to fit another one in. But just a different approach of dealing with it. Yeah. So anyway, I'll probably experiment with this too later and make some comparisons to the version I have. I could also probably install this and still use it with the other tools I have and just pull the actual state transitions from this. But yeah, they do mention how they set this up. In this beat, sorry, I'm trying to find this particular set of text. Oh yeah, so they say here, so it's a Python simulator, obviously. Yeah, they have to modify the OpenAI's framework for multi-agent domain, and then they say the sufficient implementation allows for thousands of simulation steps per second on a single thread, and then you can render it. So I don't know. I assume it. Has anyone else in the meeting actually played around with any of the book's code base or tried out any of the environments?
Not yet.
Yeah. So they meant like I'm not sure like typically with these OpenAI gym things what is considered like an efficient implementation. Like they say thousands of steps per second. I did for this environment, when I set this up, like I did just test out like at least my step functions for the environment. Right, this is the one with like two agents and more than two actions. So here, like I can run an episode, and then if I benchmark it, this is capping it at 10,000 steps. But you could see like when it runs an episode, it will record the 10,000 steps of what states were visited. These are the actions taken. So they're just saved as a tuple where each element of the tuple is an index of which action. And then now there's two reward values, right? Because each agent gets its own reward signal from the environment. But, this ran 10,000 steps in 110 microseconds. So that is like 90 million steps per second, which is way more than, thousands of steps per second. But so I don't, I wouldn't necessarily call this implementation efficient. I mean, it clearly has to handle a lot of other interface stuff with OpenAI framework. And it is using Python also, which is not going to be particularly fast. But I also don't know how relevant it is for how quickly the steps are, because when you're running this and doing training, you're typically like collecting data, and then every time you collect a new data point, you're doing like gradient updates, things with the function approximators. And each one of those steps is going to take way longer than like a single simulation step. So, I mean, if you use a different kind of algorithm where you're just trying to collect a huge amount of data from like a fixed policy and then train that for a while, then yeah, maybe it would be useful to be able to run, millions of steps per second. But usually with these algorithms, the thing that's constraining us is not like how quickly the environment step is. And I'm sure like the thousands of steps per second in the Python environment is also, perfectly adequate until we get to, there could be some type of algorithm where it would matter. But so far in this case, I don't think it does. So the other thing I can do is we could sort of see how difficult these problems are, like task one and task two. So again, like task one has just two agents and two items. Task three has three agents and three items. So here's an example of just running an episode, like a single episode. So now I'm not capping the steps, right? This is actually running to completion. And we can see here that this took, oh God, is it really 1.5 million steps? Okay, so at least for this, even this is for the easier task. So just with random behavior, it took 1.5 million steps. We can also collect some statistics on this. And what I found was that on average, it's about, it's like between 1 and 200,000 steps that, random behavior will take to get a solution, at least to this first environment. Now, for this one, for the task two with three agents and three items, it's way worse. Like here, it's 300,000 or something average. However, I've also capped every sample at 1 million steps, and we could see that it's definitely hit that cap. So the true average here is probably much higher than this number of steps. Like I'm not going to run this with an uncapped max because it would probably take a really long time to collect the data. Yeah, to calculate this. So anyway, like these are the environments. That's sort of how difficult it is that we're talking about for these things. But yeah, now that we have a sense of like what the problem actually looks like, and how many states there are, we can go back to some of the preliminary stuff in the book to introduce these techniques in the chapter. But are there any questions so far on the environment and how it works?
Good.
Okay, so I already talked about like the purpose of these techniques is to use function approximators that generalize information across states. The other thing we have to worry about is what information is available to the agents during training. And there's different versions of this. like the simplest thing that we can do, which isn't always possible, is to do some sort of centralized training. And there's different versions of centralized training. They all have the same thing in common, which is that there is some controller of the whole algorithm which can see all the information about the problem. So the state, which in this case, like the state also includes all the information about all the agents in the problem. And then it can also see the actions of all the agents and the rewards that all the agents received. And if we train where, we're going to both have that access to that information when we're training, and also when we deploy the agents, they're going to continue to have that. That would be called like centralized training and execution. Where, now central learning is a more extreme version of that, where we just reduce the entire problem to like a single agent problem, where we have all the agents and the agents all have their, actions that they can take. But we consider a central controller that will then disseminate policy to all of the agents in the problem. And in that case, we don't even really have a multi-agent problem. We just have a complicated action space where, the central agent has to worry about the joint actions of all the agents. I could show an example of that here in this section. So I have this like utility function that will take, this was like the multi-agent problem, and we can cast it as a single agent problem. And the only thing you can really see here that's different is the action space. So each agent, right, has 6 actions. So when we turn this into a central learning problem, we just have to consider all the combinations of actions. So now there's basically just 36 actions for our central agent to worry about, where, here, each one of these, it's just all the different combinations of the 2 actions. So you could see that if we try to turn this into a central learning problem, the action space grows exponentially quickly. Because then if we have 3 agents, we're going to have, like this is just 6 squared actions. But then we're going to have 6 cubed and, 6 to the 4th if we have 4 agents. The other thing we need to do to turn it into a central problem is, in general, like the agents get their own reward. But to do central learning, we have to use a single reward signal. So we have to take the joint rewards, in this case, there'd be 2 of them, 1 for each agent, and combine it into a single reward. Now here, with the way this works is I just pass a function here that combines the rewards. And the sum function is just going to take the sum. The other thing, you could also have a problem where all the agents have the same reward. That would be a common reward task where, like, whenever one agent gets a reward, that reward is just shared among all the agents. And in that case, you could just take like the first reward and use that as a single reward. So those types of problems are trivial to turn into a central learning problem. This task, the agents do get their own reward, but if, as the person training the agents, we really just care about the items getting collected, then we really just care about the collective reward between all the agents. Like, we don't care if, so that will incentivize the items that need cooperation to be collected. The items where there's competition, we may have some inefficiency where agents go after the same item, but it'll still in the long run lead to a situation where all the items are collected. So like this task, we can use the sum signal. If we really do have a competitive problem where the agents are competing, then we can't use this technique, because the each agent optimizing its own behavior is important in that case, and we can't just sum the rewards together, especially in something like a zero-sum game where the sum of rewards is always 0 by definition. This will not be a useful metric to use. So this is like I'm constructing the problem in a way where I have this joint action space, and because like the central agent has all the information, right? Like it knows exactly, it can tell both agents what to do, and it can see the outcome from both agents. But it doesn't necessarily have to be this way where we actually turn it into a single agent problem. We could also have central learning where the agents learn their own behavior. It's just that they can also see what's happening with all the other agents. And they have, basically unrestricted information about the environment. Yeah, also, so this technique where we do central learning, this also requires that when we deploy the system, the thing that is running all the agents has to continue to have access to all that information, right? Like it needs to see all the agents, be able to send simultaneously information about the actions for all the agents to take. So that's where it's centralized not only in the training, but also in the execution of the problem. So the alternative to that is that we have everything decentralized. So each individual agent can see, its own behavior, where it is, but it might have limited information about the environment. It might not be able to see the position of all the other agents, but this would all be handled just by defining the observation space of an agent. So basically, each agent will get from the environment like an observation, where the environment looks at it and says, okay, like you really only have access, to this information in the environment. And it may be everything, it may be limited. Usually when we have these observations, we also have the observation history as part of what's available to the agent. So like an agent could, if it needs to, save those observations. So it can see some history, either an unlimited history or a fixed length history of its own observations, which could include behavior of other agents. And then each agent will then try to learn something just locally within its own, available observations. And it can't interact with the other agents. This would include situations, though, where it could try to estimate things about other agents, but only from its own observations. It's like it could try to learn things about the other agents, but it wouldn't just be given that information as part of the environment. And it might be unreliable because there might be certain steps in training where it can't see what the other agents are doing, or some of them. So then, it wouldn't be able to update its belief about those agents. So independent learning, it's obviously like more scalable because each individual agent, we don't have this explosion of the action space and the information. We're basically just running a simultaneous set of individual learning. But there are some problems with completely, decentralized training. I mean, there's a problem that we're not using all the information we could have available. Like, it may be that we really don't have that information, like the environment doesn't give it to us. Oftentimes, we're choosing to do a decentralized training because we have this like explosion of the action space if we try to do central learning. So because of that, we try to limit the problem by, artificially, limiting each agent just to its own set of observations and its own
So
policy
is
function.
it possible to report the agent's findings to a centralized source or processor so they could get an understanding of what those regions are, and maybe,
So that who can get an understanding?
well, okay, you just said that you can't have a centralized,
So
you
that,
have to
yeah,
have a
that would
distributed to
be,
cut the, okay, go ahead.
yeah, that would be a version of centralized training where like, yeah, the agents, like even centralized training could choose to like only use a subset of information to direct a particular agent, but the centralized thing has access to all the information. Theory. When we do decentralized training, there is no centralized entity. Like each agent, I mean, the only thing in this case that is sort of centralized is the environment itself. Now, like in my case, if I like have the environment running on my computer and I'm running an algorithm, then it's sort of always possible to do centralized training because like all the information is there, like in the computer. Um, Now, if someone like gives you an environment that's some kind of black box where you don't have access to the environment, like all you can do with the environment, you can send it like the information, like an agent, like each individual agent, which are decentralized, could send to the environment what it's doing, and then the environment
Right.
would distribute back out to those agents. But then
That's
we're
what I'm talking about. Yeah, yeah.
yeah,
Okay.
but that like where it's truly decentralized training, that's a situation where like you as the person trying to do the training don't have access to the environment. Like all you have is that black box where, so the agents can't communicate with each other. They can communicate with the environment, right? But like they don't know how the other agents are communicating with the environment.
So what would that, if it's not centralized, if it's not decentralized, but if it was a combination, that's yet a third type, then what do you want to call that then? If it's just doesn't fit into the envelope of the other two
I mean,
types.
it's probably then just centralized, but like you can always take centralized training and restrict it somehow
Well,
down.
okay, I guess what I'm trying to understand is by its nature, decentralized means there have to be n processing regions. Otherwise, how could it be decentralized, right? So if those
Well,
n
yeah,
regions keep that information under each of its auspices, or each of the n domains don't talk to each other, well, maybe if they talk to somebody, there's some information there that's valuable that could make convergence more quick, faster, in the future, right? That's all I'm
so really
suggesting.
like yeah, so with decentralized, like really what is decentralized are the individual agents themselves. So really decentralized would just mean a case where each agent can only learn independently from anything else. The only information it has is observations from the environment. Now,
But they
the
don't
thing
all have the same environment. They have subsets of the environment, correct?
so by the environment I mean
State information.
the thing that receives the state of all the agents and then provides a transition to a new state. So it would then tell the agents like the environment is just one thing. The agents are in a particular state in the environment, right? But like in the most general definition of the environment, it will simply provide observations to the individual agents based on where they are in the environment, and then the environment itself like knows what the state is.
But the
But
environment isn't partitioned according to the agents.
no, no, like the
Okay.
environment is its own thing. It's the thing the agents are interacting with, and
All right. But then the agents don't have visibility to the entire environment, or they do.
it depends on how the problem is set up. So
Ah,
like
that's the point. To me, in a real world networking situation, you have agents and environments which are partitioned, both, and then you have a
I think
centralized.
it's just you're just sort of using a different like what you're the environment you're talking about is not the same environment in this case. Like here, the environment
Okay,
refers to the thing that has all the information, and
I
that
see, I see,
because
I see.
because the
All right, all
environment
right.
can only make a transition by having all the information.
Yeah, I'm just
Like
trying to link it to a real world problem that I'm trying to solve. That's all. But all right, I get your
yeah, I mean,
definition.
if you're dealing with like a physical system too, like then the environment really is like the actual world that has information beyond what you could even collect, but you have defined sort of something like some sort of function that pulls an observation from that environment.
Correct.
Normally, when we program this stuff, like I have the environment in the computer. So if I want to create an observation, I have to tell the environment, like, hey, like form an observation by restricting this information. In a real
Yeah.
world scenario, like that's going to be forced upon you because you may, as an agent or a training system, try to collect the observation you want from the environment that's useful, but because of physical limitations, you're only going to get a certain amount of information.
Observability. Absolutely.
Yeah. And
Absolutely.
that's going to be, in this case, just because we're dealing with things where we're simulating stuff, sometimes what looks like the environment is actually something we're controlling, but we're just using it as a model for other problems where we wouldn't be able to control it. But
Okay.
yeah, like the in yeah, but really the what the environment does is provide that transition where it provides an updated state based on what the agents are doing
Fair enough.
or attempting to do. But yeah, I mean, it
Okay.
is like the environment does need all the information, right? Because like the actual transition where you figure out like what happens next, there is like a true thing that happens next, and that is only you know computable if you have all the information. All right, and I'm including random behavior too, because like even these environments can have random transitions that are stochastic, but they still have a specific probability distribution of what happens that is
Of
based
course.
on the current state. So yeah, in a sense, like it is like they are stochastic environments, but they're fully specified stochastic environments. Um, yeah. Okay. So if it's truly decentralized, like the agents are not gonna, yeah, they're not gonna like be able to use information from other agents. And if there's some central figure that is collecting bits of information from all the agents and attempting to do something useful with that, they won't have access to that. Um, but this would be really, you would only do this like if you had to, if you were in a situation where the agents really can't communicate and there's no way, like they're running on their own isolated system, and you don't have the ability to have any kind of central system that can communicate with all of them simultaneously. The other problem is there's a lot of solutions that just can't be solved for with like independent learning, where the agents are learning independently and they don't like attempt to use information from other agents, because like there's a lot of coordination that just can't be achieved um, in this case. And also things may not converge to begin with, because the agents, if it's truly like decentralized, the agents are just attempting to like learn how to behave in the environment as if it is a well-behaved environment like you'd have in reinforcement learning. However, part of the environment now is the behavior of the other agents, right? They're affecting the environment, but they're also changing over time. So now you have a non-stationary environment, and that violates all the assumptions of reinforcement learning. So it may not, succeed at converging to anything. But oftentimes these techniques do work. Like early in the book, we showed examples of using independent learning in this like soccer game, and in the level-based foraging, the simple version of the example, where it seemed to learn something despite all of these limitations. And it's cheaper. It can be cheaper than other techniques. So, it could be worth trying. I think the other thing, maybe Fred was talking about, this is an example of another modification where during training, you could have something that is collecting information from all the agents, and maybe collecting data from all the agents, using it to train a function that helps reduce the variance of updates in the agents. So an example of that could be like if you have an actor critic method, you could have a centralized critic that is shared among all the agents that is also trained with information from all the agents. And that may be more useful than each individual agent having their own critic, which they can only train with the limited data that they've collected. And then we're only going to use that centralized information during training. The actual output of the training will still be an agent that can operate independently once it gets into the real world. The difference with fully centralized training, like with central learning here, once this is deployed, the actual deployed system needs to be a central system that can communicate with all the agents. Whereas
I would only
if
add to
we,
that not just training, but retraining to accommodate for model drift.
well, training just includes anytime
Right.
you're updating the agents.
Okay. That's fine.
Yeah. But then, we're distinguishing training from execution, where we're just deploying an agent, and it may be deployed in a more restricted environment where really, you know, they can't communicate. Like if these are autonomous vehicles or robots or something, they may not have the capacity to communicate with each other. So then they're just stuck with behaving according, like they're still getting observations. they're using those observations with their policy function to make decisions, but part of their actual decision-making function cannot be something that depends on, centralized information. But the centralized information could have been used to update the policies during training.
Exactly.
And that is, that's very common as well.
Yeah. Okay.
Yeah. Okay. So now, there's a few just comments on notation. Typically, we're going to look at both value function methods and policy function methods. And different books use different parameters. Like here, they're using this phi symbol for the policy parameters and theta for the value function parameters. I think it's a little confusing because I think in the Sutton and Bartow book, they use theta for the policy parameters and W for the value parameters. But another way to distinguish it is that when we write the policy function, we use pi. So anytime you see a parameter inside of a pi function, this is a policy function. Inside of v, this is a value function. Again, like value function methods try to learn action values, which is, the value an agent expects to receive in the long run if it takes a particular action. Usually, once we learn the value function, an agent would just try to select an action with a higher value or the action with the highest value. And that method can work. It has a lot of limitations in approximation. It cannot learn policies that actually require a specific sort of random behavior. Whereas a policy function is something where it actually defines a probability distribution over actions for a particular state. And it could be any distribution. It could have specific probabilities for different actions. And this, we learn about this in ordinary reinforcement learning as well, that policy gradient methods do have a lot of advantages in the realm of approximation. They can sometimes be more expensive methods, though, or it can be a little trickier to get them to converge. But, we can always try both of them and see what works better. And also usually policy methods usually also use a value function for the critic in a lot of actor critic methods, which is actually necessary if you have, unless you want to use a method where you have to run an episode to completion before you do anything. And we can see that like for this problem, right, I showed how this task took like, 100 something thousand steps or even a million steps to complete. So that there's a lot of environments where that's not feasible because you just have to wait too long. So yeah, usually we do need both of these functions available. Now, yeah, for the, like, it's true that we could have access to the full state information. Where again, like the state is just all the information about the environment at a particular time step. Like in the level-based foraging example, I showed like, oh yeah, sorry. So here's an episode, right? So these are like when we talk about the state, this is all the state information, all right? The agent positions, etc. So this is like what the environment has access to. And all of this information is necessary to produce a new state when we see what the actions are of the agents. But when we talk about the more general problem, the agents can get observations and also histories of observations. So this would be like at any particular time step, like t, an agent in theory has access to this whole observation history, from the beginning to here. And that may be all the information the agent has, available to it. Yeah, now it could, but we could also set up the problem where each individual agent has the full state information of the problem. And that would be like, again, only possible where we're doing centralized learning. But usually we will, for more complicated problems, need to define some observation function. Now, another thing that's kind of hard to actually see from the book's code base is how they actually make use of this observation history. Because, if you're doing function approximation and you have something like, a neural net, it's usually going to have some kind of fixed, input that you're working with. And having this growing observation history can be really challenging to deal with. I mean, you can deal with it by just using the most recent observation. Oh yeah, this observation history can also include the actions of other agents as well, which is not something you have even in the state. So if the problem meets certain criteria and is really well behaved, it's possible that the state itself, which is the full information about the environment, is sufficient to do training. But in general, we also need like the history of the other agents' actions, but the observation history can also include that. Yeah, but they make this note here. In a fully observable environment, agents can use the state of the environment instead of the individual joint observation history. Yeah, so yeah, joint observation history would, yeah, that's the other question, is like whether the agents even have access to, there's all these different layers of how much information is shareable, because you also might need the agents to even have access to the observation history of the other agents, right? Because that might affect, if they're trying to model their behavior somehow, they also have to understand the information that those agents have had access to. So it can get really complicated, but at least for the initial experiments and stuff people do, we're just going to stick with actually using the state itself. And well, I'll get to it in a second, but to actually run any of these approximation techniques, you do have to figure out how you want to use either the state or the observation history in your function approximation. And that, it's not really mentioned here in the book, but that step is also a way to sort of define and limit what information the agents have available to them.
Can I ask a quick question?
Uh-huh.
So when you're defining the state, how do you map that to a feature vector or a multidimensional feature vector that's used in this training?
Yeah, we're gonna get to that.
All right.
Yep.
I'll
yeah.
stand by. All right,
yeah.
Thank you.
So the first set of algorithms we're gonna look. So actually, why don't we can just talk about that now. So the book, as we can see in this section, it just jumps straight to independent learning, right? This is where we reduce the problem. We have each agent attempt to learn on its own value and policy function. In chapter 6, I think, we actually started out with central learning, which is also mentioned earlier in this chapter. What they don't really go into here is doing central learning with approximation, but I think that's sort of the easiest first thing to look at with these problems. So yeah, why don't we start with that? So in order to do, what Fred said, in order to do any of this, we do need to map whatever information we have, whether it's the state or the observation history, into a feature vector. And there's a whole discussion. So when you're using neural nets and nonlinear approximation, there's not that much effort put into this, because we just kind of want to dump the information in the simplest way and let the network, figure it out. If we're doing linear approximation, there's much more importance in creating feature vectors that are useful. I had showed, let's see, in this, maybe not here. Well, anyway, so we can look at the state here. So there's different ways of converting this into a feature vector. We have XY coordinates for the agents and items. So, one option is just to make like a dense feature vector where, we want to normalize the positions. So here we have like a maximum size of the grid. So here it's 15 by 15. So we could sort of map the X and Y coordinates to some, floating point value between like -1 and 1, for example, and just concatenate all the positions together. Then we have the levels, we have to worry about. We can also sort of normalize these to the maximum level and also concatenate them as just like a normalized value from 0 to 1, and then the fractions are just how high is the level relative to the max level. So that's one way of doing things. Now, that type of feature vector mapping, where we're just like having all the dense information, probably is only going to work at all even with some sort of neural network approximation. Because especially when you have things like the levels, like think about the relationship of the levels to the behavior. Like it has to check whether a level is high enough, or if they need to combine the levels of two different agents to collect an item. And that is sort of like a logical evaluation. It's not something a linear function could do because we're combining information and we're just storing it as like an actual, value where like we could sort of see if it's greater than or less than. But that to actually, if you were writing a program for this agent behavior, you would have like conditional statements on whether or not the level is adequate. And that type of logic is not something that a linear function is going to be able to do. If we have a complicated enough neural network, it could probably figure that out, unravel that information. And remember, at least for central learning, it's going to have to then map that to a policy, which is going to be a policy over the joint action space. So there's 36 actions, which are the combined actions of the two different agents. Now, the other way you could think about this is because the grid is fixed, right? It's 15 by 15. Really, each grid position is a distinct point in the grid. So we could just try to create a sparse feature vector where we just encode with like 0 or 1 whether an agent is in that position on the grid, right? So we could take the grid and say, okay, it's 15 by 15. That's like the number of grid spots. And then we could have like a vector that's 15 by 15 long for each agent. And we could just indicate in that vector, where it is in the grid. And then same with the items. And then with the levels, we could also make sparse representations of the levels, where we have like the max level is 4, let's say. So we could just take for each item and concatenate like a length 4 vector, where there's just a one hot value in there depending on what the level is. Now, if we do that, then we've really encoded all of the information about the state. Like at a bit level, like we have preserved all the state information. Now, how to untangle that into what the policy is might be difficult, but there might even be a chance of a linear function accomplishing that if we really have this sparse representation. And then there's other ways that you could do it too. I don't actually know. So for the book, they show eventually an example of them solving this problem with really only one algorithm. So they mention this, right? This is a value function algorithm. We talked about DQN earlier. This is independent DQN. It's just the DQN algorithm where, like, the nice thing about these independent algorithms is there's really nothing new in them related to the multi-agent problem. We're just doing DQN, but we just have n sets of everything, right? So we have n sets of parameters, n replay buffers, right? One for each agent. And we just go through and each agent just acts as its own DQN learner. The only thing we have to do that's different is we have to, right, apply the joint actions and get the joint rewards from the environment. This like one step is where we have to use the multi-agent environment. Every other part of the algorithm is just the same as DQN. And actually, same with the actor critic. This looks a little more complicated because we have, not only is there n networks corresponding, there's one network for each agent. They also have k parallel environments. This is, you don't have to do this because there's also, of course, an independent actor critic algorithm without synchronous environments. Synchronous environments are just a way to leverage hardware better, where basically each agent is just going to have k simultaneous trajectories through the environment that it can see. And then it can do learning in just a batch update with each environment. But this, in the DQN algorithm, we also do batch learning, but we don't have parallel environments. Instead, we have this replay buffer where we store past experience from interacting with the environment. And then when we create a batch, we just sample from the replay buffer some amount of data. And then that's used for a gradient update. But this one is different in that we actually have these. I mean, this is a more stable way of learning in general because all of the batch data we're getting, it's actually from these parallel interactions with the environment. All those interactions are happening with the current policies. So this is an on policy method where all the data we're collecting is reflective of the current agent policies that are being used. Whereas here, when we use a replay buffer with DQN, we have, past data in the buffer. And this problem is even worse with multi-agent independent DQN because normally you have to worry about the data becoming irrelevant from the current policy. Like it might not reflect accurately the current policy. With this, the buffer is also affected by the other agent's behavior. So it may not, the data in the buffer might be irrelevant, not just relative to your own policy, but based on the policy of the other agents. You don't have that same kind of problem with this algorithm, which is probably why this is the only algorithm they actually present an experiment with for this, right? This is the first task I showed and the second task. Obviously showing here that the second task being much harder, the convergence is way slower. This is quite a bit of training, right? This is 40 million training steps for this plot. They said it took, what do they say? 3 hours to train this with whatever they were doing with this simultaneous actor critic algorithm. Anyway, this is an independent learning method. So we could also try to do this by converting it to a central problem. Here, even though they did this, right, they don't mention in the book anywhere here how they actually form the feature vector, like what they do. What we can see from the code base, right, how the observation is formed, get observation space, and assuming that it just gets the unrestricted observation where it can see everything. And then I don't think the code base actually has an example of this particular experiment and what kind of actor critic agent they're using. I'm guessing though, from what the information here, that they just concatenate everything in the observation space and maybe they normalize it. I'm not sure, but that would be akin to the dense feature vector I mentioned. But we can see what this looks like with the sparse feature. So I made versions of both. We can see what it looks like. So here, if I want to sort of make a sparse feature vector, what I have to do is I give it the width and the height of the environment. And this is like, there's n agents, m items, and then the max level for both. And what I'm doing here is like calculating how many features total there is, right? And it's just the number of agents, and then you have to add up all the dimensions, right? So you have the width, the height, the max level, same for the items. And then all this stuff, what it's doing is just figuring out, which features in the vector are active. Right? So this happens to be like a sparse representation where I'm not actually storing the whole feature vector with a bunch of zeros. I'm just storing the features that happen to be active. And by active, there's only one possible value they have, which is 1. This you can also have pretty efficient implementations of the function approximator with these sparse features, because you don't have to do dot products, full dot products. All you have to do is add up the active features in the problem. But what this function does, like here I've run it, what it does is it creates an example of the feature vector, this binary feature vector, and then it provides a function to update it. And the way the update function works, so here's, I just run like, this is just a test episode in the environment. So there's all these states. So we can see now what I'm doing here is I'm running the update function, the update feature vector function, on the first state in the episode. And we can see this is the feature vector it produces. So there's 12 features, right? Because there's 3 different dimensions of data for the 2 agents and 2 items, right? So 4 times 3 is 12. And then, right, so there's only, these are the 12 active features in the environment. And there's 132 total features. So if this was like a full vector you wrote out, it would have length 132. But effectively only 12, of the spots in it or actually have anything in them. And then the other thing you can see here, so this is the feature vector update on, this episode concluded after 353,000 steps or so. This is the terminal state. Notice the reason this is the terminal state is because both items have been collected, right? It's indicated here, true and true. So now I just to sort of test this is working correctly. This is now the feature vector of the terminal state. And now there's only 6 active features because the way I designed it is just when an item is collected, it's just none of its features can be active. So its position and level just turn off. And then I don't even bother to, right? Like notice that these are still the same values. These are the values for the position and level of the item, but they're just not going to be treated because they're past the 6 active features. So it's only going to look at the first 6 active features in this case. Okay, so any questions about the like sparse feature vector? How it works?
So when you're creating a sparse feature vector, I would think that it would be the vector that contains the greatest amount of information and is
Yeah, I mean
is the leanest, but maybe that's not the right way of saying it. But I think you get the point. The entropy would be highest, right?
yeah, I mean
For that. So
this.
how are
Yeah,
you guaranteeing that in your method?
yeah. I mean, in theory, like this feature vector does like have the full state information. Yeah, like because like you can look at the states here. Like this state is simple enough, right? This environment, we have these discrete grid positions. Unlike another environment where you might have continuous positions. If you have continuous positions, then you're stuck. Like you can't, you
Right.
could discretize it and make it sparse, but then you're losing information. You could leave the coordinates as numbers, but because we have a discrete grid, right? There's only so many bits in the state. So actually, right there. So the sparse feature vector has length 132. So the number of bits is like 2 to the 132. Obviously, that's too many states to handle, but the feature vector provides the relevant information. It's just that it's the reason why it's not a tabular problem, right? If it was a tabular problem, the feature vector we make would be small enough that we could just say, let's not even worry about the feature vector. Let's just estimate each state individually. Here, now, like the number of states in this problem is not actually 2 to the 132 because there's a lot of those feature vectors don't exist, right? Like only some of them are actually possible.
Right.
But the point is it has the capacity to store the full information about any state in the problem.
Okay, but I guess the way you made the predetermination that those other states don't exist, what was the method that? was
Oh,
used
I
for
I
that?
didn't. Well, no, I mean I didn't determine like. Well, what do you mean? Like this 132 features is like whatever state I provide it, it maps to a unique feature vector.
Okay, so you just made an assumption that not all those states are populated.
Well, what do you mean? All the states are you talking about the features in the
The
vector?
the the features in the vector, right?
Well, I just have a clear definition of what it means for a feature to be active. Like the x position, like x is 1 to 15. So it'll just turn on whatever the appropriate x is
Yeah,
for that
that was
particular
your
feature.
rule. I missed that part. Okay,
Yeah.
so I thought there was some empirical way of
No, no.
determining that
I'm just yeah. I'm just saying like right there.
mathematically.
Yeah.
Okay,
There's 15. Just however long this is in each direction.
yeah.
Right. I'm just basically indicating like it's there. It's in position 5. It's in position 4. You know.
All right. But do
So
you know of any techniques for doing that kind of reduction without making the definition up front like you did here? Are there ways, are there tools or techniques to do that?
I mean, this is doing it here. You mean like I mean, it's just a certain logic of you mean a technique to do the mapping or to actually for the to form like the like the actual type of the feature vector
Well, determining which
make
of when you have a reduced vector, right, as you're using here, right, it means you're leaving out data that's insignificant generally, right, not as in
oh
the
no
case here.
actually
Right.
it so yeah so it's not leaving any information out. It's just that some of the features are on which correspond to the state, right, like the position. um right, like this is the state information, right, so 9, 13, 1, 1, 6, 6, 7, 9. So all of these numbers will control which element is turned on in the feature vector. But right, there's only like 12 things here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10,
Right,
11.
right, right. In
So
your
there's
example,
basically 12 relevant pieces of information per state.
yeah, that's the way
And
you
that
defined
those
it here. Right. Okay.
well, no, that I mean this state is from the environment. So like this is the actual state,
Okay.
right? Like this is the state from the environment. This has nothing to do with the feature vector yet. This is actually the full information. And then I'm mapping it here to these active features. The ones that are 0 are just features that are not turned on. So instead of storing the zeros, you just ignore them, right?
Mhm.
And all you have to take note of is which values are not 0.
Fair enough.
Yeah. In a typical, most languages, including this language, Julia, also has a sparse array object. Those generally work by just storing which values are non-zero, and then they have the values themselves. This is simpler than a sparse array because the only possible non-zero values are 1. It can't be another value. So I'm basically just storing like a bit vector here.
I understand. I was thinking about a more general case, and that's fine. I don't want to get ahead of us. Let's keep
Yeah.
going.
So you can also define a dense feature vector, which is a little simpler. This is the one where I talked about where you just sort of normalize the x and y position. Again, we're still going to have 12 values. So just as a comparison, this is like the same thing, but now mapping it to the dense feature vector, where this is actually now a vector of 12 values, where it's the position and level of the agents and items in the environment. And then this is the terminal one where now these values are 0 because the item is gone. So you'd see like in this case now I have the information, but now it's an actual numerical value. And that then has to be computed in some way
Right.
appropriately. And so the success of the method will depend upon how well the function is at translating this into what it needs. Like I said, this, like a linear function, has very little shot of taking this information and figuring out, which item is collectible by, itself or other agents. Yeah. But, there's a lot of other complications that can happen with sparse feature vectors. You kind of have to just do the experiment and see which one is more successful. You can always just try out both methods.
Right.
But here, yeah, so if I do central learning, so this is just, if we reduce this to a central learning problem, right, the whole point is we convert it into just a Markov decision process, right? Like this sum function where we sum the rewards. So now this is a well-defined task for just ordinary reinforcement learning. We don't need any multi-agent techniques, assuming that, like the central agent is now controlling all of the sub-agents. The problem is, though, the action space starts getting big. Here it's already 36, and it will get much larger as we add more agents.
Right.
We can still try to see if this task is solvable. Now, I didn't have enough time to do really thorough experiments with this, but here's some examples of running this. These are just, each one of these things is just a different method from ordinary reinforcement learning. This is like a method with eligibility traces. And we could see here, at least like the central methods I tried so far did not seem to be successful at solving this, but I said I didn't experiment that long with this. It's worth, I'll look at this a little more later and see what, if any, central learning methods can actually succeed at this. Again, you have to learn, which is this a linear? Yeah, so here's a linear, I'll show a more typical. So here's an example of a linear approximator with this. We can see that the parameter matrix, right, it has 12 rows and 36 columns. The 12 rows are for, when we multiply the feature vectors of length 12 for this problem. But because this is a method that learns action values, it has 36 columns corresponding to, like, it has to have a different value for all the 36 actions. And to be successful, it has to collect enough data really from all of the actions to actually distinguish them. So you can just imagine how much data. Like here I ran this for 1 million steps. And I think in the book, right, they had some success with this, running it for like 40 million steps. And this is with independent learning, where the action space is smaller, right? Each agent only has 6 actions. So I would suspect, if you believe the authors, that a central learning method, even though it might run faster, like per step, would require a lot more training data to actually learn. And so this is just a linear method, obviously. Like I don't think the linear method will work to begin with on this problem. And then you do it with this is a nonlinear method where now there's all these different weight matrices for the neural network. But again, this might have a chance of working, but then also requires probably even more training data
Right.
to succeed. And then you could also use any of the single agent policy gradient methods on this. Again, same problem. You have to learn a policy function, which learns a distribution over 36 actions, a lot harder than over 6 actions. You have the same data problem. But, this is sort of pending further evaluation whether a central learning method can work. And then if the book does the experiment with an actor-critic method, I also did, at least so far, the only thing I've implemented as far as independent methods is this independent DQN method, which again, this is the multi-agent variation of just the DQN algorithm, where you could see here, now the value parameters now, it just looks like DQN, but now we have tuples of things instead of the original things. So right, we have n copies, n different sets of parameters, and then also different, right, n different sets of replay buffers. But otherwise, we're just learning right, individual policies for each agent. So here's an example of independent DQN. So notice now what we end up training here is 2 different parameter matrices, one for each agent. But notice how now each one only has 6 columns corresponding to the 6 actions instead of 36. So here, there's a lot less data to actually learn. But again, you have the problem with it being non-stationary, other issues again, this is showing, this is a linear, I mean, I didn't have time to run this very long and experiment with different hyperparameters.
Right.
But here, this is showing, actually, if we run this multiple times, we can see, yeah, usually, like it hasn't really learned anything, right? Because I capped the steps at 100,000. Here, it's not succeeding. I mean, occasionally it goes faster, but that's probably just random. Usually it's not accomplishing anything. Here's a, oh yeah, but by the way, for this also, I'm using the dense feature vector. I also tried it with the sparse one. It didn't work very well either. Here's a neural net version. I'm just copying what they said in the book of having 2 layers of size 64 each. Now, actually, this this is sort of new. I was just looking at this, but this seems to actually be somewhat learning something, because, I mean, if it finished in, I mean, sometimes it's failing, but more often than not, it actually is completing the task in less, well, it doesn't have that much success, but this could also train a lot longer. It's also, some of the tasks also are harder than others. So when you're randomly sampling examples, like in this case, there's 2 items that are each level 4. And both of these items require both agents to coordinate to collect them. So this just initial state is much harder to deal with than some of the others. But here, both items can be collected by an individual agent. So again, like the agents probably learn how to collect items because we're doing independent learning. There's no coordination between the agents. They could learn coordination just through the algorithm, and you're sort of relying on some coincidence. But the most likely thing for this to learn quickly is situations where an agent can just collect an item on its own. And those are the times where this actually succeeds in a limited number of steps. Not, okay, well, here's a task where, see, it took a while, like 4,000 steps is not great, but this actually has an item that requires both agents to coordinate to solve. So, some success. Again, this is like showing, like here, because it's independent learning, right? Each agent has its own sort of action value it's evaluating. So, right, when we deploy this, each agent is just operating independently with its own policy function. So later on, I'll probably try to implement the actor-critic version, see if that scales any better, see if the central learning works. But yeah, I was mostly just trying to get all these utility functions working that is required for doing the independent learning. But I would like to see if, yeah, I can replicate this in the book, because again, like there's not much information here about what they did. Like I don't know what the feature vector is. They didn't do DQN, and there's not much. There's a little bit of hyperparameter information, but there's still more things. So I would sort of like to see how these charts compare with DQN and then central learning too, and see how it scales with difficulty. But yeah, that's more, also probably need that information for future tasks in the book. But this chapter is very long. For people that were interested in this book and this topic, this is probably the chapter that you are interested in, because this is the chapter that covers modern approximation techniques for solving multi-agent problems, which has not been covered at all up to this point. But because this is sort of the main topic that people are interested in, it's also, the way this book is organized, all of that is in this one chapter. So, like, I feel like normally this chapter would be like 5 different chapters. If you go through it, this one chapter covers every single technique in modern multi-agent learning. So, well, it's the topic people are probably most interested in. It's also going to take the longest to get through and sort of build everything up. But so far we just touched on independence learning, which is really just another version of a single agent reduction, where the agents are just operating independently. And then it's not until later where we get to techniques where there's actually coordination between the agents, and they all the stuff we had already talked about. But in the tabular problem, we're gonna have to try to extend to this. So I don't know. Hopefully next time we'll move on with some of these next sections, and hopefully I'll have more insight into this level-based foraging problem and how easily it can be solved by different techniques.
So, by independent agents, it just means that, both agents have their own, their own policy functions, that don't have any interaction between each other, which, later I know that the critic, there's, the idea of having a common critic in order to have communication between each other, but that's later.
Yeah, I mean, the common critic is pretty easy to add to this. That would just be an example of this mode where we have some degree of centralization with training, but the actual agents that are trained then can operate independently still, right? Like the central critic is just used for training, and then they just have it available. It doesn't. Yeah, like they then have the policy function that they just use when the agents are deployed. But later on, we'll get into more complicated algorithms where the agents actually try to learn about the other agents. Like agent modeling is one thing, and then there's just any of the sort of game theory techniques we talked about before will come later, right? Because like all of the game theory type techniques involve the agents either knowing information about the other agents or making assumptions about it somehow and like modeling things. And then the actions they decide are actually based on their coordination with the other agents rather than just treating the other agents as part of the environment, which is so far all these things we looked at today, these like independent DQN, really this is just the agents are just they're just taking the other agents as part of the environment. They're not assuming there's anything, there's nothing to learn about them other than their behavior will influence what happens in the environment. But we're just trying to learn sort of an average of what that looks like.
Is this book in electronic form? Is there a link on that homepage that has a book in electronic form?
There's a link in the meeting description.
In the meetings. Okay. All right. Thank you.
And in the slide deck, the meeting description, and the YouTube videos, there should be links everywhere to that stuff. Yeah, because I also made that there's a slide deck you can get a link to on, I think, meeting description and YouTube videos.
Okay, great.
Yeah,
thank you.
And also the link where the book also has links to the code base and this other stuff. Yeah, and the meeting description will also have links to these notebooks and the code I've written.